Hey everyone. So our next topic for the subject solid mensurations are circles, sectors, and segments. So let's proceed. So we have the first topic that is circles. So what are circles? So a circle is a set of points, and each of which is equidistant from a fixed point called center. So probably you have an idea of what are the basic parts of a circle. You have radius and the diameter, where the diameter is twice the radius. And the radius is the line segment that's joining the center of a circle to any point on the circle. And that's called the radius. And then the interior of the circle is the set of all points within the boundary of the circle, whose distances from the center is always less than the measure of the diameter. So that's the interior of the circle. Then exterior of the circle, set of all points outside the boundary of the circle, whose distances from the center is always greater than the measure of the radius. And an arc is a portion of a circle that contains two endpoints on the circle, okay? And all points on the circle between these endpoints. So two arcs are formed. So if you're going to consider this one, okay, we can call that a minor arc. But then if you're going to consider the outer part, that gives us the major arc. So major arc is the longer arc, this one, and the minor arc is the shorter arc. So probably this one at the bottom. Okay. Then you have this chord. Okay, so chord is a line segment joining any 2 points on the circle, and it divides the circle in two regions or segments. So that is the minor segment and the major segment. And the diameter of a circle is the chord that passes through the center. Okay, and it is known as the longest chord and is twice the length of the radius. So an inscribed angle is an angle whose vertex lies on the circle and whose sides are chords of the circle. So probably inscribed angle. Okay, so if I'm going to draw a chord here and another chord, let's say here. Okay, so that is called the interior angle. Then this one, you have the tangent line. So a line that is the same plane on the circle is a tangent line of the circle. If it intersects the circle at exactly one point on the circle. So let's say line L. Okay, so it intersects at point P, right, at one point or a single point on the circle. So that's called a tangent line. Okay, so we have the second line if it intersects 2 points on the circle. So let's say line M. Okay, so it intersects the circle at 2 points, at point here and here. So this is called a second line. So two circles are tangent. Okay, tangent circles if they are tangent to the same line at the same point. So we have two, which is internally tangent and externally tangent. So we have internally tangent, that is their centers, they both lie on one side of their common tangent. Okay, and then externally tangent, their centers are on the opposite sides of their common tangent line. Okay, so this one, okay, so externally tangent, okay, so it is opposite of their common tangent lines on both sides. And then if this is one, okay, on the same side, probably, right? So internally and externally tangent. Some formulas on circles, you have the area and circumference probably. So let's deal with circumference. So the circumference of a circle is the perimeter of the circle. So it can be obtained by the formula. Okay, so C is the circumference, and then R is simply the radius, and pi is the constant value, which is equivalent to 3 point approximately 3.14. Right? So you have this formula. So you can use 2 pi r, or you can use pi nd. So this is the diameter. So where r and d is the radius, which is r, and diameter d respectively, and c is the circumference. So the area of the circle is determined by its radius. Thus, if the length of the radius is given, one can always obtain the area of the circle. Similarly for semicircle and quarter circle. So let's try this formula. So we have area of circle, given radius, you can use this formula, pi r squared, or if given diameter of the circle, you can use this formula, pi d squared all over 4. Okay, so we have area for semicircle, that is half a circle. Okay, so given radius, you divide the area of a circle to 2. So you have 1/2 pi r squared. And a quarter circle, you can divide the area of the circle by 4. So you'll have a formula of 1/4 pi r squared all over 4. Okay? Or 1/4 pi r squared. Okay? Then area of an annulus region, you have this one. Okay, so the larger circle, okay, the area of the larger circle minus the area of the smaller circle. So if the circles of different radii have common center, then they are referred to as concentric circles. So that's same center. And the area bounded by any two concentric circles is known as the annulus. And then the shaded region in the figure is called the annulus region. So you have this formula. Okay, so it factored out pi since it is common. Uh, Value on both of the area of the larger circle minus the area of the smaller circle. So let's try some illustrative problems. So problem 1, determine the circumference of the area and the area of a circle whose radii is 5 millimeters. So you need to determine the circumference and the area, and its radius is 5 millimeters. So you have a given of 5 millimeters for radius, and the required is the circumference and the area of the circle. So you have the solution, solving for the circumference. So circumference has a formula of, call this 2 pi r if given radius, and pi d if you are given as diameter. Since we are given as radius, which is 5, we can use circumference equals 2 pi r. Okay, then substituting the value of the radius, we have 5, and then simplifying this one, we'll get 10 pi millimeters, okay, based on the unit. And you can also use a decimal value, okay, so that gives us 31.42 millimeters. So either of these two answers are probably correct. And solving for the area of the uh, circle, we have this formula, pi r squared if given radius, or pi d squared all over 4 if given diameter. So since radius is given, I could use this formula. Okay, so substituting the value of your radius, have pi 5 squared. That gives us 25 pi square millimeters. So that is for area. Or you can use decimal point, 2 decimal places. So that gives us 78.54 square millimeters. So next problem, problem number 2. The area of a circle is 25 pi square meters. Determine its circumference. So based on the problem, we have the given, which is the area, that is 25 pi square meters. And then the required or the unknown is you need to determine for its circumference. Okay, so possible solution, we'll be using the uh, given, which is area. Okay, so solving for the area using the formula for the area, by solving for the radius using the area formula, you have this pi r squared. Okay, so substituting the value of your area, which is 25 pi, and that is equal to pi r squared. and dividing both sides by pi. Okay? Then taking the square root of both sides, you can solve for the radius, which is 5 meters. Now I have this radius. We can now use the formula for circumference. Okay, so solving for the circumference, we have 2 pi r. Okay, you have the formula for the circumference, and substituting the value of the radius, you get 2 pi and 5 for the radius. Using your calculator, you can compute that one. That is 10 pi meters, or you can use decimal value. Okay? So problem number 3. The distances between any two centers, okay, of the three coplanar circles that are externally tangent, okay, to each other are 20, 24, and 28 centimeters. So find the area of the three circles. So based on the given, you have uh, three circles that are externally tangent. Okay? And the distances between any two centers are 20, 24, and 28. So based on the given, okay, you could draw that one, three circles, okay, then externally tangent, okay, and then you have the centers, so distances of their centers, which is 20, 24, and 28. So just draw that one. Okay, you can get this possible figure. Okay, so there are three circles. Okay, circle 1, which is C1, circle 2, and then circle 3. And then their centers are denoted as A, B, and then C. Okay, so they are all externally tangent to each other. So this here. Then the distances between any two centers is given as 20, 24, and 28. Okay, and then what is the required? The area of the three circles, okay, which is area for C1, which is A1, area for C2, circle 2, and then area of the circle or third circle, which is A3. Okay. So based on the given, okay, I could use this uh, triangle probably, triangle ABC, which is 20, 24, and 28. Okay, so based on that, I could get this one, but then take note that A, okay, so from center of C1, which is at point A, up to the distance on the circle is probably radius 1, right? And also similarly for point B or center up to the distance at this point, right? That gives us R2, right? So that is the radius of a second circle. Similarly, radius of second circle, which is R2, and probably this one is R3 for the third circle. And this is also R3, and this is R1. Right? So we can say that R1 plus R2, right, which is for C2, and then it will be equal to 20. And similarly, R2 plus R3, okay, radius 3, is equivalent to 24. Similarly, R1 plus R3 is 28. Okay, so based on that, we can say that R1, which is for circle 1, right, and then plus R2 is equal to 20. Similarly, this is R2 and R3. So this is R2, R3, right, based on this one. So we can say that R2, R3, okay, is 24. And then R1 plus R3, this one, this side, is 28. So we can say that these are equations 1, 2, and 3. Okay. Then from equation 1, based on this equation, we can solve for, let's say R1. Right? So solving for R1, okay, So you can subtract both sides by R2. Okay? So you get an answer of R1 is equivalent to 20 minus R2. And this gives us equation 1a. Okay? So it came from equation 1. Okay? Now, I'll just use equation 3 probably. Right? So I'll just substitute the value of a1 or the equation 1a to equation 3, which is this one. So from equation 3, we have R1 plus R3 equals 28. And the value of R1 is 20 minus R2. So I'll just change this one to 20 minus R2. So that's it. 20 minus R2 is R1. That is from equation 1a. And then plus R3 is equivalent to 28. So simplifying this one, we get negative R2 plus R3 is equivalent to 8. And that gives us, let's say this is equation 4. Okay. Now, next step will be, we will be adding equation 3, which we haven't used yet, and the new equation 4. Okay. So we need to add those two. Okay. Now, using equation 4 and then equation 2. Okay, so we add equation 2 and equation 4. So equation 2 is R2 plus R3, 24. And then equation 4 is negative R2 plus R3 equal to 8. So add them now. We have R2 plus negative R2. So that gives us positive negative. So that gives us negative. So R2 minus R2 is 0. So you get 2R3. And this is, I think, 32. So 2R3 equals 32. Then solving for R3, you need to divide that one, both sides by 2. So R3 now is 16 centimeters. So the radius for the third circle, which is C3, is 16 centimeters. Okay. Now, you have equation 4 or 2, just 2. Okay, so substitute the value of R3 to equation 2. So I'll just use this one. We have R3 as 16. So from equation 2, R2 plus R3 equals 24. Okay. And then substituting R3. So you'll get R2 plus 16 equals 24. Then simplifying that one, R2 is 8 centimeters. So the radius for the C2, this one, is 8 centimeters. Okay. Now, lastly, we need to solve for R1. So I could substitute R2 to equation 1a. Okay, so you could solve for R1, which is, we have R2 here. So probably we get R1 equals 20 R2. Okay, 20 minus R2. Then R2 is 8. So I'll just substitute 8 here. Okay, so that gives us R1 equals 20 minus 8. And R1 is 12 centimeters. So now we have all the radii for those given circles. Okay, we can now solve for the area of each of the circles. You have radius 1, 12 centimeters, 2 is 8, and 3 is 16. So continuation of our solution. So radius for C1, radius for C2, and then radius for the third circle C3. Using the formula solving for A1, we have pi r squared. So A1 is equivalent to pi, radius 1, then squared. Right? Then substituting radius 1, which is 12. So you get 144 pi square centimeters. And solving for A2, using similar formula, so A2 is equivalent to pi r2 squared. Right? Then substituting radius of 2, which is 8 centimeter. Okay, so you get 64 pi square centimeters. And lastly, for the third circle, which has a radius of 16, okay, so you can use the same formula, pi r squared. So radius is 3, Okay, so 16 R3 for the third radius. So substituting that value 16 square pi, so you get an answer of 256 square centimeters. So those are the area, okay, of each of the circles. Okay, so area 1, 2, and 3. Now, next topic is sectors and segments. Okay, so the sector is a figure bounded by two radii and an occluded arc. Okay, which is the arc is denoted as S, which is called arc length, and theta is the central angle, and these are 0, 2 radii. Right? So the central angle uh, is measured in radians as noted here and using this formula. This formula is used to solve for the arc length S. Okay, and this has been discussed in your trigonometry subjects. Okay, so you have arc length is equivalent to radius multiplied by theta, which is the central angle, and it is measured in radians. So take note of that. Okay, then we have the area of a sector. We have two formula here. You have 1/2 radius and the arc length. So RS, radius, and S, or the arc length. And then you have also 1/2 R squared, then theta. Theta is always measured in radians when you're computing for the area of the sector. Okay, so take note of those formula. So the area of the segment. So area of segment is equal to the area of sector formed by the arc and the central angle subtended on the same arc minus the area of the triangle formed by the two radii and the central angle. So you have this formula. So 1/2 r squared, where r is the radius, okay, and theta here is in radians, and sine theta, which is the central angle. So sine theta should be in degree, right? So this formula is derived from the area of the sector, which is the whole, right, minus the area of the triangle, and the segment is computed here, which is the shaded area. Okay, so hopefully that's clear. Area of the sector, right, minus area of the triangle. Some illustrated problems. So find the area of sector bounded by a central angle which is 60 degrees in a circle of radius 5 centimeters. So based on the given, you are given central angle which is 60 and the radius of 5. So 60 degrees and 5 centimeters. So area of the sector, right? So that's the required area of a given sector. Now, solution. We could solve for the area of the sector using the formula based on the given r theta. So that is r squared theta. Okay, so 1/2 r squared theta, but theta should be in okay, radians. So for that one, we need to first convert the angle to radian. That is theta is equivalent to 60 degrees and conversion factor, okay, to get the unit of radian. So you multiply that one by pi all over 180 degrees, so rad, and then simplifying this one, you get pi all over 3 radians. Then we can now substitute the given value. Area is 1/2, r is 5, which is 5 here, 5 square, and theta is pi all over 3. Simplifying that one, you get 13.09 square centimeters. Now, circle has an area of 144 pi square centimeters. Okay, so circle, okay, is cut into two segments by a chord that is 6 centimeters from the center of the circle. So what is the area of the smaller segment? So take note, if a chord passes to a circle, okay, or a chord is drawn on a circle, okay, you always have a two segments, which is the major and the minor, which is the bigger and the smaller segment. So based on the given, you have the area, which is 144 pi square centimeters. That is the area for the circle, and a chord that is 6 centimeters from the center of the circle. So based on the given, you have the area, which is 144 pi square centimeters, and you may need to draw the given figure. So take note of that one, which is a chord that is 6 centimeters from the center of the circle. So based on the given, to draw this one, okay? So you have now, this would be the center of the circle, and probably this is the radius, and also this one. And the chord is drawn, okay, which is 6 centimeters, okay, from the center. So the 6 here now is from the center up to the chord, and theta all over 2 is this angle, okay? And the whole angle here is the central angle theta, so that is divided into two equal or congruent value. You get theta all over 2, okay? So the required is the area of the smaller segment, okay? So probably this one, this area here above smaller segment, okay? That's the area of the smaller segment. Using a formula, we can solve the radius based on the given value here, which is the area of the circle, right? So solving for the radius, using the formula of the circle, substituting the area, which is 144 pi, okay, dividing both sides by pi, that gives us 144, then taking square root, you get 12 centimeters. So now we can now use this sector here, right? And also the triangle. So taking the figure of the smaller segment, this one, okay, we have 6, which is this, and then theta all over 2, and then that is the radius, which is 12, okay? So we are determining for the area of the smaller segment, okay? Based on that one, that is the area of the sector, which is the whole, minus area of the smaller minus the area of the triangle, okay? So this one is the unknown. Now next step probably is we need to get the uh, triangle here, right, in order for us to solve for uh, the central angle theta, right? So I have taken this triangle here, right triangle, okay? Then solving for theta, okay, you can use a function which is cosine. This is the adjacent and this is the hypotenuse, okay? Solving for the central angle, I'll just use cosine. Okay, theta all over 2 is equivalent to 6, which is adjacent, right? All over 12, which is the hypotenuse. Then simplifying that one, taking arc, dividing both sides by cosine, you get uh, arc cosine here, then 6 all over 12. And then you can multiply to both sides. Okay? And then theta now is 120 degrees. So 120 degrees is from this side, which is the radius, up to the radius here. Right? So theta. Now, we can solve for the area of the smaller segment using the formula of area of the triangle, or area of the sector, minus area of the segment, which is given as 1/2 r squared, and the theta minus sine theta. But take note, for theta alone, central angle should be in radians. Okay, but then sine theta here, we can use theta as degrees, which is 120. So sine 120 degrees. But this one, we need to convert this. So theta now is 120, then pi rad. So they get 2 pi all over 3 radians. Then we can now substitute the given value. R is 12. Okay. Theta here is 2 pi, 2 pi all over 3. And then minus sine, right? 120 degrees, which is this one. Okay, so take note of this substitution here. Okay. Then simplifying that one, we'll get an answer of 88.44 square centimeters. So this is the area of the uh, smaller segment, which is this one. So next problem, find the area of the segment bounded by a 50-degree central angle in a circle of radius 2 millimeters. Okay, so based on the given, you have central angle, radius, and we need to determine area of the segment. So given radius and central angle, and the required is the area of the segment. So solution, we can use the formula for the area of a segment, which is area of the sector minus area of the what you call this triangle. Okay, so for that we need to convert, okay, 50 degrees to the region. Okay, so that we use that one. So 50 degrees and then pi rad, okay, pi rad all over 180. Simplifying that one, that gives us 5 pi all over 18 rad. Then using the formula, 1/2 r squared, then theta, which is this one, uh, pi, 5 pi all over 18 minus sine 50 degrees. Okay, so this one. Simplifying that one using your calculator, right, you get an answer of 0.213 square millimeters. So additional information. Okay, so inscribe and circumscribe polygon. So you may need to familiarize yourself with those terms, inscribe and circumscribe. So a polygon is inscribed in a circle if the vertices of the polygon lie on the circle. So the polygon is inscribed in a circle. So probably the polygon is inside, okay, a circle, where the vertices of the polygon lie on the circle. Technically, this is a square that is inscribed. So a square is inscribed in a circle, this one. Okay? So any polygon, so a pentagon is inscribed. So probably pentagon is inside a circle, right? Now for the circumscribe, if each side of the polygon is tangent to the circle, then the polygon is circumscribed about the circle. So this time around, the circle is inside the given polygon. So the polygon, let's say hexagon, the hexagon is circumscribed about the circle. So probably this is the given figure. So again, polygon is any n-sided polygon. It can be a square or what you call this, heptagon, decagon, and so on. Okay. So polygon is circumscribed about the circle, this one. Okay, so you should familiarize yourself with those terms. Now, radius of the circle, circumscribing a triangle. Okay, so the formula here we have radius r, okay, is equivalent to ABC, or product of the sides of the triangle, all over 4 times the area of the triangle. Okay, so as shown here, using Heron's formula, where S is the semi-perimeter. Okay, familiar with this one. And technically, when the problem is stating this one, the figure should be this. And 3 sides of the triangle are given, and you need to determine for the radius of the circle. Right? So you have A, B, and C. And then uh, take note of the formula for Heron's. Okay, so this particular topic, we are simply solving for the area. Okay, sometimes you need to solve for the unknown side using this formula, okay, and so on. And then radius of the circle inscribed in a triangle. You have this formula, which is the radius is equivalent to A, or area of the triangle, over S. Or you can simplify that one using this formula. So this equation here, or formula, is also similar to the one above. And take note that S is always the semi-perimeter of the triangle. So that now the circle is inside, right? So A, B, and C. Okay. So this is the problem. Let's try some problems. The area of a circle is 36 pi square meters. Okay. So what is the length of a regular octagon circumscribe about the circle? I circumscribe about the circle. So hopefully you're familiar with that one. So based on the given, the area of circle is 36 pi, and then a regular octagon, which is circumscribe about the circle. Okay. So based on the given, circumscribe about. Okay. So circle is tangent on all sides. Okay. So we can say that the red line here is the radius of the circle. Okay. And then here, that is the side of the octagon, is S. And also the area is given for the circle. So we can determine for the area, I mean, or the radius of the circle. So the required is the side of the regular octagon, which is S. Okay. So based on the given, we can solve for the radius, right? And we can get the triangle, right? This side here, right? So based on the triangle, we have radius. Then we all know that this is the central angle, but then it is divided into two equal or congruent value, similarly with the side. So from this point up to the vertex, that gives us S all over 2. Similarly on the other side, S all over 2. This is theta all over 2, and similarly this is theta all over 2. And then we can solve for radius, which is also equal to the apotem. Okay, if you're familiar with the properties of a regular polygon. Okay. Solving for the radius using the area, which is 36 pi. Okay, so substitute that value here. We get 36 pi is equivalent to pi r squared. So radius is 6 meters. Okay, and that is also equivalent to the apotem. Now, solving for the central angle, you have 360 degrees all over n. Okay, so for the central angle. And since it is octagon, you have 8 sides, and that will give us a value of 45 degrees for the central angle. Okay. Now, solving for the side of your polygon using this right triangle, this one. Okay. Have here, you have theta all over 2, this is r, and that is s all over 2. Okay, so using a tangent function based on this given angle, okay, you have adjacent, okay, and this one is opposite. So tangent function is opposite, which is s all over 2, all over adjacent side, which is r, right? Then simplifying that one, you get s all over 2r. And then we have theta, which is 45. We have r, which is 6. We can solve for s. So s now is equivalent to 2r tangent theta all over 2. So substituting those values, you get 2 multiplied by 6, and then tangent 45 all over 2. So s now is 4.97 meters. So that is the side of your regular polygon. So problem number 8. The radius of a circle is 1000 inches. So find the apotem of a regular pentagon inscribed in a circle. Okay, so inscribe is inside the circle. Then B, the length of side of the regular pentagon. Right, so regular pentagon, and then the area of the regular pentagon. So based on the given, you have radius of 1000, and a regular pentagon is inscribed in a circle, so inside the circle. And then you're familiar with this one. So that is the apotem, the red line here, and those are the radius. And the side of the pentagon is denoted as S. Okay, and then radius is 1000. Now we have three unknowns, which is the apotem, the length of the side, and then probably the area, right, of the pentagon. Okay, so based on the given, we have radius. Okay, we can solve for central angle probably. Okay, so we can take this triangle first. Okay, so that triangle. But then I rotated this triangle already here. Okay, so since you have the apotem, okay, which is drawn perpendicular to this side, okay, and that side is divided into two equal segments, which is s all over 2, and this one is also s all over 2, okay, and then theta all over 2 is also divided into two congruent angles, which is theta all over 2, and this is theta all over 2 also. Okay, so solving for the central angle theta, five-sided, so 360 divided by 5, right, gives us this. So theta now is 72 degrees. So we have the value of theta here. Since radius is given, we can take that right triangle. Okay. So solving for the side of the polygon using a right triangle, this triangle here, okay, or probably the other side around, we can use that one. So that's a right triangle. I have used a sine function. You are solving for the side, which is the opposite. Okay. So sine theta all over 2 is equivalent to opposite, which is s all over 2 all over r, which is hypotenuse, based on the right triangle. So that gives simplifying that one, you'll get s all over 2r, and that is 2r sine theta all over 2. So r is 1000 and theta is 72 degrees. So you get 1175.57 inches for the side, okay, of the polygon. So we have solved one of the unknown here. Similarly, we can use the formula for the cosine function in order for us to solve for the apotem this time. So probably this one is the apotem. Right? So apotem A all over R. So simplifying that one, similar to this uh, procedure, you can get cosine, which is adjacent based on this given angle. This is the adjacent side A all over the hypotenuse R. Hypotenuse R, okay? So you get 1000 cosine 72 all over 5, okay? And that I all over 2, I mean. So you get an apotem measurement of 809.02 inches. So that's the apotem. Now solving for the area, okay, you can use the 1/2 PA, where PA or P is NS, so 1/2 NSA. And you have the number of sides, which is 5. S is 1175.57, and then A is apotem, which is 809.02. Substituting those values, you get 1/2, 5, 1175.57, and 809.02. Simplifying that using your calculator, the area of the pentagon is 2,377,649.10 square inches. So I guess that's it. So thank you for attending this session. So next topic will be more on plane figures.